Hey everyone, welcome to the Algebra 2 Module 3 Topic 1 review. This is the unit that's all about inverse functions, radical functions, and solving equations with radicals in them. So it's kind of all about square roots pretty much. But there's other things that we did. It's kind of a hodgepodge of a bunch of stuff, okay? And so the first thing we started with at the very, very beginning was we were asked to, after we had dealt with, like in module 2 at the end of it, all of these power functions, all different ways to rewrite and have all these functions that have multiple x's in them, right? More than x squared. We graphed all of those. We found key characteristics. And then we were like, all right, let's graph the inverse of them, whatever that means. All right. And so by the way that we defined inverse for inverse functions is that if we have f of x being our output, right? The thing that we plug something into and it spits out a value, with x being our input, well, then the inverse of a function simply means to swap the inputs and outputs around. We're swapping x and y around. So if we invert something, invert it, that means now f of x in our original function is our input and x is our output. Okay, so we're going to swap x and essentially y, right? F of x is the same as y. And so what that means graphically, what we're going to do with these functions to graph their inverse is right now I have some plots or points that are already plotted on my graph. And these are x, y values, right? They're coordinate plane values. And so this one looks to be at 0, 4, for instance, right? X is 4 or x is 0 and y is 4. Well, if I'm going to invert that, that simply means I need to swap these around. I need to replace x with y. And so if this is at 0, 4 on my new function, I guess I'll graph it in blue. I'll have the inverse of this be blue. I need to graph the point 4, 0. Right? I'm just swapping x and y around. All right, so I'm going to do that for all of them. I'm going to do that for this one here too. This is at -1, 1. That means I need to graph a point at 1, -1, which is going to be right here. And then this point's at -2, or sorry, 0, -2, which means I need to plot a point at 2, 0. And now I kind of see the pattern. Now I kind of see where this thing is going. And so I'm going to follow kind of the same pattern here. And now that means that these dots are now dots on my inverted function, like so. And there I've done. I've graphed it. Okay. Now, is the original graph a function? Well, we know that something's a function when it passes the vertical line test, meaning if I draw an up and down line, a straight up vertical line, any point on this graph, I even tried to do the straight line tool and I still made it crooked. If I draw a vertical line across my graph and it ever crosses more than once over the top of my curve, then I know it's not a function. But in this case, I think I'm in the clear. Like if I scan anywhere left to right, I'm going to be okay. I don't cross it more than once. So yes, the original graph is a function, the red one that I have here, because, well, the real definition is every input has exactly one output. But that's also the vertical line test. That's what it's asking, right? You pick a spot for the vertical line. That's your input. You check if you have only one output, okay? Well, here's the thing. If we're inverting functions, then all of a sudden we're swapping inputs and outputs. And so if I'm inverting this around and I look at my new graph, we run into an issue, right? As soon as I place a vertical line over the top of it, I'm realizing that no matter where I put this thing, if I have an input there, I'm going to cross it more than once. So is the inverse a function? No, it's not. This is in blue. It's not. No, because it fails the vertical line test, or VLT, which really means there's an input. And in fact, there's infinitely many in this case, but you only have to have one bad egg. There's an input that has more than one output. And so because this thing is basically looping over itself, it's not a function. All right, so let's do the same thing here. This one's graphed in blue, and we're going to invert it. And so we're going to use the same tactic. Currently, we have these points in their original form. We're going to swap x and y around. So for instance, this one's at 0, comma 1. Sorry, 1, comma 0. I'm already doing the swapping in my head. 1, comma 0. That means I need to graph a point at 0, 1 right here. Okay, so that's going to be on my thing. Then I have this point right here at 2, comma 1. That means I need to graph a point at 1, comma 2. All right. This one is at 0, negative 1. That means I need to put a point at negative 1, 0. Okay. So now I have my 3 middle points plotted, these 3 right here, and I need to now just do these to kind of figure out what's the shape of this thing going to look like. And so this one looks to be at 9, comma 2. Sorry, no. Yeah, 9, comma 2, right? That means I'm going to have a point at 2, comma 9, like this. So that's my inverted point, 2, comma 9. And then this one's going to be at negative 7, it looks like, negative 2. That means I need to put a point at negative 2, negative 7. So negative 2, negative 7. And now my inverted function is the function that goes through these dots, like so. Cool. So I've basically just, swapped x and y. We've inverted it, right? We've swapped input and output. All right, is the original graph a function? Yes. It passes the VLT. Passes vertical line tests. There's no place I could draw an up and down line that crosses this blue graph more than once. You might be like, well, what about right down the middle right here, right? What if I draw a point right at this thing right here? And that's tricky. That is tricky. But we actually still do only have one value there. It looks to be like straight up and down, which it kind of is, but only for one split second, only for that one singular point. Okay, so this is in fact still a function. It's okay. And then when we invert it, we run into the same thing, except for this time everything's nice, right? I can cross it only one time across my graph. So same logic. Is the inverse a function? Also, yes, the inverse is a function. It passes the VLT. It passes the vertical line test, or every input has one output. Okay, so we talked about how we invert graphs. We just swap x and y. Well, what about inverting equations? What does that mean? What does that do? And so right now we have f of x equals 2x plus 8. But I know that to invert a function, inverting a function means swapping f of x and x, right? We're swapping the input and the output. Now, for sake of clarity, I'm going to use f of x and replace it with y again. We're going to go back or roll back the years a little bit, replace f of x back with y. And that's just because we're going to be doing some algebra to solve for y. And when we have f of x written out as like a variable, it looks kind of weird. So I'm going to rewrite this as y equals 2x plus 8. And then we're going to invert it. So I'm going to swap y with x, meaning this is going to come x equals 2y plus 8. Now, in order to figure out what the inverse actually is, we still need to solve for y. So we're going to invert the function, swap x and y, then solve for y. Meaning I'm going to do things to both sides to get y by itself. So the first thing I see is I need to get rid of this 8. So I'm going to subtract 8 from both sides. I get x minus 8 equals 2y. And then I'm going to divide by 2. And I get y equals, let's say, x over 2 minus 4. Okay. So these two right now are inverses. We've swapped x and y, and we've solved for y. Okay. So if I put these on a graph, these two would be inverses of each other. X and y would be swapped. I guess I could pull up Desmos and show you. But we actually have another way of checking this. And I'm going to need maybe some extra space here. We have another way of checking this, and it's by using the composition of functions. Okay, so we did this a few days, composing functions and checking if they're inverses or not. And so here's the definition again. So we have this little bullet point: inverting function means swapping x and y. If we want to check using composition of functions if two functions are inverted, well, then here's how we do it. If we say that f of x, sorry, I wrote that wrong, f of x and g of x are inverses, if f and x and g of f are inverses, then f of g of x, meaning if I plug in a function in for the input, that has to be equal to g of f of x, which has to be equal to x. Whoa, what the heck? What does that mean? Okay, let's see. Let's plug this stuff in. Okay, so first of all, we have to be a little bit aware of what these compositions really mean and what's breaking it down. Okay, so here's what it, like, by definition, a composition of functions means. If you were to rewrite this, f of g of x, is how I would read that, f of g of x, that would mean you take f of x, and every time you see x, like the variable x, you substitute the entire function of g of x. So substitute with g of x. All right. So what does that mean? Let's go back to here. So both of these are called y right now. Let's call one of them f of x and one of them g of x. All right. I'm going to move this stuff up a little bit here. See if we can give myself some more room. So I'm going to swap back x and y and call this one f of x. That's my original function. And then my inverse function, I'm going to call g of x. Just names for the function. And here's maybe why you would use function notation, by the way, instead of x and y. So what this means is, if I want to rewrite f of g of x, that means every time I see an x in f of x, which I see one right here next to the 2, I have to substitute it with this entire function. Okay? So let's see what that means. Let's see what that does. I'm going to rewrite f of x, although I guess I won't write the left side. I'm just going to rewrite this thing right here, f of x. But every time I see an x, instead of writing that, I'm going to write in this entire function. So instead of 2 times x, it's going to become 2 times x over 2 minus 4, and then plus 8 at the end, because that was already up here. This is f of g of x, right? Instead of writing 2x, I've written 2 times g of x. I've substituted in that function, okay? Well, let's check. What does this equal? If I multiply this out, I get 2 times x over 2 is x. 2 times negative 4 is negative 8, and then plus 8. Oh, well, these cancel. So that means that f of g of x equals x. All right? F of g of x equals x. Maybe rewrite this a little better. This thing multiplies out to 2x over 2 minus 8 plus 8. Well, that just simplifies to x. Okay? Let's go the other way. So remember, by the definition, f of g of x has to equal x. That's good. So far, right? We plug this in. Everything canceled except for the x. That's good. That means I think we inverted it correctly. Let's check g of f of x. Now what that means is take my function g, except every time I see x, replace it with the entire function of f of x. And so it's going to become this. X instead of x over 2. Let me do this over here. Instead of x over 2, it's going to be 2x plus 8 over 2, and then minus 4. Well, if I do this out, if I divide this, I can divide this and this, and then this and this. Well, here, let me just rewrite it like this. Let me go one step at a time. This will be 2x over 2 plus 8 over 2 minus 4. 2x over 2 is just x. 8 over 2 is just 4 minus 4. Those cancel, and I get x. So that means that, yes, f of g of x and g of f of x, if I plug in that function for that variable, everything cancels out, and I get x. So these are, in fact, inverses. All right. Let's try this one. So first step, I got to invert the function, meaning swap x and y. Let's replace this with y real quick, but we're going to go back in a second. So here's my function. If I want to invert it, that means I have to swap x with y and y with x. All right. And now I need to solve for x. Solve for y. The only way to do that is to cancel out this square root, meaning I got to take the square root of both sides. And I get y minus 5 equals the square root of x. Okay. Now, here's where we have to kind of recall something from the beginning of the unit. This thing says state any necessary domain restrictions. What does that mean? Well, take a look back at this original function. This thing right here is a quadratic. In fact, it's pretty close to what we have down here, except for this is really like x plus 2, quantity squared. Then when we went to invert this thing, when we went to swap x and y, it no longer became a function, right? This thing failed the vertical line test. And so what we could do, instead of saying that we're going to invert every single point on this function, maybe we only invert the upper half of this graph. Maybe we only care about the points that are going to leave us with a function left over once we invert it, right? Once we flip it on its side. And so normally when we take the square root of both sides, we have to consider the positive and the negative version of that variable, right? There's two ways to multiply something together by itself. You can have a negative times a negative or a positive times a positive. That's where this plus or minus comes from. But because we want to remain a function, because we want to invert this thing and have it be a function, I'm actually only going to choose the positive version this time. I'm going to just say forget about the negative. Okay, so that means we're going to restrict the domain. Oh my gosh, I'm running out of ink. I'm running out of RAM on my laptop. I have so much writing. Restrict the domain. If I erase all of this, will you be mad at me? I think I'm going to have to erase all of this. I'm not going to lie. Okay, so you have this here. Take a mental snapshot or a screenshot. The cool thing about this is you can just rewind the video and it appears back again for you. Okay, although, okay, I'm just going to erase all this, but I'm going to leave that little mark there so that you can we can use the same space. Okay, I'm going to erase all of this just to save me some ink. I might even erase all these. We're not going to go back to the, oh, dang it. I got to erase all this. Get out of here. If I put too much ink on the page, it just makes my computer lag, and then it won't let me draw quickly. And then it will lag, and my handwriting will look bad. And I never want to have bad handwriting. Okay, so I'm restricting the domain. Oh, look at how nice that is. Never mind, it's still bad. Restrict domain to x is greater than 0. I'm going to just do, it says greater than equal to 0. All the positive values. Okay, and restrict domain to x is greater than equal to 0. Then I need to solve for y. That means I can add 5 to both sides. 5 plus 5. And that means I get y equals the positive square root of x plus 5. Okay? Now, once again, that is my inverted function. So I'm going to rename this one again to g of x, my inverted function. And then this one, my original one, is f of x. So let's try our plugging stuff in and composing the functions. I need to do f of g of x. That means every time I see an x in my function, I'm going to replace it with this whole thing, x, the square root of x plus 5. And so here's what we get. If I plug in f of g of x, or sometimes you'll see it written like this, f and then a little o in between, and then g, kind of looks like fog. F of g, F-O-G, you'll get this. The square value, or I'm going to quantity square, instead of x, I'm going to do the square root of x plus 5, and then minus 5 squared. And then when I go to simplify this, these two cancel out, and I'm left with just the square root of x squared, which, as we know, these two cancel, and I'm left with just x. So check, that works. We're halfway there. Now let's try GOF, GOF. That means I need to replace this x in g of x with this function. So I get the square root of x minus 5 quantity squared, and then plus 5. Well, if I square root a square, that means they cancel, and so I'm left with x minus 5 plus 5. These two cancel, and you get only x, which means f of g equals g o f equals x, which means they are, in fact, inverses. All right, that's a lot of hodgepodge. That is quite a lot of mumbo jumbo. All right, but this inverting thing in composing functions is kind of cool. All right, we're done with page 1. Only 3 more to go. Here we go. Well, is it 4? Oh my gosh, it is 4. All right, here we go. I might save some of the problems at the end. I might not do them all. We'll see. All right, transformations. In fact, I think we're, at least in my class, I feel pretty good about transformations. So I'm going to use this simply as notes. And so I'm going to just go I'm going to go sideways. I'm going to turn my paper sideways. Feel free to turn your phone sideways or whatever you want here. And I'm going to write in this little area, like right here and right here. Okay, I'm going to write in here. Oh, this is weird because now my stuff is all on the side. All right, here we go. Let's try it. So I'm just going to write the transformation form of the equation for any function. Label what each of the letters does, and then all you have to do, maybe we could do a few of these, and maybe we could sketch a little graph, and talk about what each transformation is, okay? So here we go. If we're going to transform f of x, so transforming any function f of x, just any function called f of x, is going to look like this. The first thing we can do is we can throw a big old A in front, and then we're going to multiply by our function f of, we can go with b right here, b times, in parentheses, oops, this should be black, in parentheses, x minus c, and then close that off, plus d. All right, we have A, B, C, and D. Those are the 4 things that you can do to a function. Here's what each does, okay? A, like we've seen many, many times throughout our math careers, it dilates or stretches or compresses, whatever words you want to use, and it reflects vertically reflects if negative. Awesome. You know, it can make our thing grow faster or smaller, changes how it grows, it dilates it, it stretches it, shrinks it, and then if it's negative, it flips it upside down. All right, this one, B, is the new one. This is kind of what has been introduced in this unit that you might not have seen before. Although we do kind of do it. What? We do it in a couple different units. But B also dilates, but to a different degree. That degree, I don't know. It's like weird. It depends on the function. That's the weird part. It dilates, but the important thing, the thing that you really need to know, at least for the scope of this class right now, and you'll get more into it in pre-calc, is that B kind of does the same thing as A, except it horizontally reflects if it's negative. It horizontally reflects if it's negative. Okay, so it dilates things still, makes things grow faster or smaller. And then if it's negative, it's going to flip it left to right or right to left. All right, then we have C, good old-fashioned C. This is going to be our horizontal translation. You've done this before. Horizontal translation. I'm already running out of ink. Horizontal meaning left to right. Except for we have to know that the weird thing happens with the horizontal translation, the C value. Left is when I add, and right is when I subtract, okay, inside the actual function. We're used to that at this point. I talked to my Algebra 1 students about it. This is the first time they've learned the opposite thing, and I gave them 9 lives. I say, you can mess this up 9 times in your life, but then after that, you cannot mess it up anymore. And so most of you probably have ran out of your lives. And so we're at the point where you can't mess it up anymore, all right? You got to know left is plus and right is minus. But for the vertical translation, which is D, vertical translation, that one follows the rules. That one goes up/down, and you go up when you add and down when you subtract. All right. How weird does that look? I don't know. Maybe that's easy to read. Maybe it's hard to read. You can just turn your phone sideways, you know. And so here's what we got to do for this. I might leave the graphing to you because you can actually just use Desmos and sketch it if you want, or a graphing calculator. I'm not going to be too picky with it. Our parent function is just whatever is happening to x. In this case, we're taking the cube root of it. And so we know the parent function for cube root of x looks something like this. That was really bad. Let me draw better. We actually did it on the front page. You go through the center 3 dots kind of like this, and then you're just cubing each of the things. So it should be -2, -8, and +2, +8. And so it looks something like this is the parent function. This is the cube root of x. But here's the transformations. The first thing is we have a dilation by a factor of 2. That's because of this 2 right here out front. Then we have a c value. It's inside the function. That's how we know it's one of the c values. It's inside the cube root in this case. It's subtracting 4. That means we're going to go right 4. Or you can say translate right 4 units or something. But anyway. And then at the end here we have a +1. That's my d value. So that means up 1. Okay. And so here's what I'm going to do. To move this thing around, to kind of sketch it, I'm going to take some of these points. I know I'm going to move them right 4. So I know this one's going to go like over here. And then we're going to have these ones kind of be here. And then I'm going to shift them up 1, which means now I'm going to go through like these 3 points. Right here, and right here. And then I'm going to dilate by a factor of 2, which kind of just means stretch it, right? Make it grow steeper. And so I'm just going to kind of just make it look, oops, that was bad. Move it around and then just kind of make it steeper, if that makes sense. So this little red graph is my sketch. It doesn't have to be perfect. I just really care more about the transformations, and then you can kind of eyeball and sketch the graph. Okay. I think you can do the next one. It's the square root of x. Square root of x looks like this. All right, cool. Let's get into these ones, simplifying each expression. All right. I'm going to erase my ink again. So just go back in the video if you need it. Simplifying each expression. So I need to know, first things first, I need to know my perfect squares. I gotta know my perfect squares. And so I might just draw a little table here. Do some perfect squares real quick. Boop, 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 boop. I got 1 up top, or my regular numbers up top. And then we'll do the square of them underneath. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, 64, the Minecraft number, 81, and 100. Oh, you thought I was slow, huh? Oh, you thought I didn't know that off the dome, huh? I could keep going. 121, 144. Maybe I'm a little slow. 169, 196, 225. And that's all I got. I got 1 through 15. But I got those ones down. Maybe except for 144. All right, so why do I need my perfect squares? Because if I want to simplify a square, but it doesn't have a nice square root, like for example, the square root of 32, then what I need to do is rewrite this term, this number that's inside a square root, as the product of a perfect square times something else, times a whole number. So basically, I need to find the largest perfect square factor that 32 has, right? And so really the first things first is I'm going to split all these up. One cool thing we can do, if everything is multiplied under a square root, I can just simplify, or not really simplify, I can break them all up like this. So I can rewrite this as the square root of 32 times the square root of x to the 4th times the square root of y to the 7th. Okay? Well, the square root of 32, I want to rewrite this by finding the largest perfect square, this largest thing on the bottom that goes into 32. And the number that I see right off the rip, I think is going to be 16. I notice that 32 is 16 times 2. And so I'm going to rewrite it as the square root of 16 times the square root of 2. Okay? And then the rest I'm just going to leave right here. Actually, no, we'll do that in a second. Then, if I take in the square root of a variable, okay, one thing we know is that the square root of x is equal to x to the 1/2 power, right? And more generally, if I have the square root of anything, and maybe not just the square root, but let's call it the nth root. So the nth root of something to the m power, that's going to be x to the m over n, like so. The square root, we just don't write it, but it has a little 2 inside the notch. And so that means each of these is really being raised to the 1/2 power. This is x to the 4th to the 1/2. This is y to the 7th to the 1/2, which we know is just x to the thing you're raising the power to over the index, which means that this really becomes x to the 4 over 2, right? The square root is the 1/2 power. This is the 4th power. When we raise a power to a power, we multiply, and so we can convert it like this, and this becomes y to the 7 over 2. Okay? I promise we're simplifying it. I promise things will get better. But here we go. And so here's where we end up. I know what the square root of 16 is. That's why I chose one of these perfect squares. I know that this is just equal to 4. Okay? So I have 4 times the square root of 2. X to the 4 over 2 is really just x squared. So times x squared times y to the 7/2. Well, that doesn't really simplify nicely, so I might actually just rewrite it as y, the square root of y to the 7th. Okay? Then what I can do is I can multiply all these things that are outside a square root and all these things that are inside a square root and kind of just merge them all together. And so here's what happens. I get 4 times x squared, which is 4x squared, out front, not in the square root. And then, because I'm multiplying everything, I can multiply by 2 times y to the 7th inside the square root. And there's my simplified answer. Okay, there's my simplified answer. So I did this in like a breakdown that took a long time. Like I broke everything down. But let's do the next one, and I think we'll actually see it's not as bad as I made it. And you can take some mental shortcuts if you want. Okay? So this time we're actually taking the cube root of 27 times x to the 6, y to the 12. And the cube root is something to the 1/3 power. So the cube root of x is equal to x to the 1/3. Okay? Now, we can't really do our perfect square thing anymore because we're not talking about square roots. We're talking about cube roots. But what's lucky about this one is that 27 is actually what we call a perfect cube because it's something times itself, okay? It's a number times a number times a number, that being the same number. And that's, in fact, 3. 3 times 3 is 9. 9 times 3 is 27, which means the cube root of 27 is just 3. So this turns into regular old 3. Then I know that this is x to the 6 over 3, and this is y to the 12th over 3. Well, that simplifies to 3 out front. X to the 6 over 3 is x squared, and y to the 12 over 3 is y to the 4th. And there's my answer. And that's simplified. That one's not too bad. Okay, what about these ones then? These ones are kind of different. Well, here's what I can do. I can multiply everything that's outside a square root together and everything that's inside of a square root together. And so I'm just going to start with that on D. I guess I skipped C. Let's go to D first, I guess. So I'm going to multiply 4 times 7. That's 28. And then I'm going to multiply 3 times 6 inside a square root. That's the square root of 18. Okay? Well, now we're going to go back to my perfect squares thing. Anytime I have a square root, if there's a perfect square that can go into that number, I can simplify it. And here's how. This 28 just stays out front, but this 18, I can break this down as the square root of 9 times the square root of 2. I know the square root of 9 is just equal to 3, so this becomes 28 times 3 times the square root of 2. Well, that's going to be what? 24 plus 60, 84 square roots of 2. And that's my answer. That's kind of interesting. That's kind of cool. All right. What about these ones that we're adding? Well, if we're adding or subtracting, like we do in C and E, we need to know that we can only add like terms. We can only add and subtract like terms. Normally, a like term is like things with X in them. But in this case, a like term is anything that has the same radical attached to it. And so look at this. If I have 4 square roots of 3 plus 7 square roots of 3, really what I'm asking is how many square roots of 3 do I have? Well, I have 4 plus 7 of them. That's 11 square roots of 3. And that's it. We simplified it, right? I just added the two like terms. These two things both have the square root of 3 attached to them, and so they're like terms. I have 11 of them in total, 4 plus 7. Okay? Well, what about this? Well, notice in E, I have some things that are to the third, or multiplied times the square root of 3, and some things that are multiplied times the square root of 5. I can only add these two things together, the 2 with the cube or the square root of 3, and I can only add these two things with the square root of 5. And so let's do that. Let's count up how many of each we have. I have 5 square roots of 3 minus 2 square roots of 3. And then I have 3 square roots of 5 plus 11 square roots of 5. Okay. Well, 5 minus 2 is 3. So I have 3 square roots of 3 plus 3 plus 11 is 14 square roots of 5. And then I have no more like terms, which means I'm done. That's it. I've simplified it. Nice. Okay, cool. We're good there. We simplified by combining like terms. The multiplication ones are actually, I think, a little bit trickier than the addition ones. All right. I'll do a couple of these. We'll solve them. But I think so far also you guys are kind of cooling on this. But maybe I'll do A and I'll do D. Okay. A and D. So when you look at A, our whole thing is that we need to get X by itself, right? We need to get X by itself. If I can get X by itself, then I've solved the equation. And so in order to do that, I normally need to get rid of some of these radicals, okay? And so the way that we do that is kind of by using that same rule that we talked about in the last problem. If I have the fourth root of like 5x minus 1 in this case, to cancel this thing out, to cancel out the fourth root, I know that this is really the same thing as 5x minus 1 to the 1/4 power, right? I could rewrite it like that. If I want to get rid of that fraction, well, I need to do the opposite of 1/4, which is multiply by 4. And if I'm multiplying exponents together, that's the same as raising it to a power of 4. And so really what I want to do to both sides is a complicated way of saying, I'm just going to raise both sides to the 4th power. That's a legal move. I can do that. As long as I do it to both sides evenly, I can do it. And what happens there is the 4th root cancels with the 4th power, and I'm left with 5x minus 1 equals 2 to the 4th, which is 2 times 2 times 2 times 2, which is 16. Okay. Then I just have to add 1 to both sides. To get x by itself, we get 5x equals 17, and then divide by 5. X equals 17 over 5. I think that's right, at least. Maybe I'm wrong. 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16. I think I'm right, but even though it's a weird fraction answer. Well, here's how we can check if we got the right answer. Let's plug it in to my original equation in for x now that we know the value of it and see if it works out. And so I'm going to go into my handy dandy TI-84, okay? Detached LCD. All right. Here's how we get to the fourth root if you've ever seen it before. So on your calculator, you can type math. This one underneath the green button, alpha. And then if you look at number 5, oops, come back, please. If you look at number 5, all the way down here, it has this little X in the index, the notch. Click that one. You can type in anything you want. And so we're going to type in the fourth root of 5. Oh, yeah, I think it's going to work out. 5 times 17 over 5, and then minus 1. If I hit enter on this, it should equal 2. It equals 2. We did it. So this checks out. So this checks. We worked. All right. Let's try. I guess I should try maybe C. I should try maybe C. Yeah, sure. Although this one gets funky. D gets funky too. So maybe we'll do that one too. Maybe I'll do all of them. Who knows? No, I don't want to do all of them. All right. So then when I get to this one, the first things first, I need to, if I want to cancel this radical, I need to square both sides. But the problem is if I square things right now, it's going to get messy. So I want to isolate my radical first. I want to get this by itself first, meaning I'm going to subtract 7. And then I'll get the square root of 10x minus 1 equals negative 12. And then I'm going to square both sides. Then I'll get 10x minus 1 equals negative 12 squared is negative 12 times negative 12, which means I get positive 144. Uh-oh, some alarm bells should be ringing. Then I'm going to add 1 to both sides. I get 10x equals 145. Divide both sides by 10. And I get x equals 145 over 10. Or 14.5. I don't know, whatever you want to say. Let's just say x equals 14.5. Okay. Let's check it. Let's see if we got it right. This one feels a little bit wrong. So let's see. I'm going to go back to my calculator here. And I'm going to type in my original equation, but except I know now x equals, what is it, 144 something? 14.5. Oops. Boop, beep, bop, boop, go away. All right, so plug this in, but replace x with 14.5. That's going to be the square root, so right here, of 10 times 14.5 minus 1, and then plus 7. That should be equal to negative 5. Uh-oh. It's not. And here's why. We did actually everything correctly. Our algebra is totally correct. The problem is there was a step. We had a step right here. The step that said the square root of 10x minus 1 equals negative 12. Well, we know that when I take the square root of a positive number, there's no way that that thing can turn negative, right? There's no way to take the square root of anything and have it be negative unless you're dealing with imaginary numbers, which in this case, we don't want to deal with. At least I don't want to deal with. And so we did all of this algebra correctly, but really what we got is this answer that doesn't satisfy the equation. It's not really a solution. It is algebraically correct, but it's not in the actual terms of the equation. And so we call this an extraneous solution. It's something that made sense in the context of the problem. We did everything right, but the problem is that we squared a negative number, which then gave us a positive, which let us solve for a positive x, but this thing can never be negative. The square root of something can never be negative. And so this is an extraneous solution. All right. I'm going to start up D, and then I'm going to call it good. So the only thing we can really do is take the square of both sides, okay? And so I'm going to get x plus 3 quantity squared equals 4x plus 9, right? These things cancel. But I still have to square everything on this side. Please, 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 please. I know some of you are actually freshmen that are watching this. You are not allowed to freshman dream this, okay? You are not allowed to freshman dream this. This thing is not x squared plus 9. Because remember, when you square a binomial, a two-term thing, you got to do this thing times itself, x plus 3 times x plus 3, which means you have to multiply x times x, and 3 times x, and this x times 3, and this 3 times 3. You got to multiply 4 things together, right? You can use the little area model if you like it, but personally, I just like to know the binomial expansion theorem, obviously, which if you know Pascal's triangle, it goes like this, 1, 2, 1. Well, guess what? These are the terms of a binomial or a trinomial or a quadnomial that's been expanded. It's been squared. Isn't that sick? Or no, it's a binomial to the power of whatever rung in the ladder you're at on the Pascal's triangle. I'm going off a weird tangent, but it's kind of cool. Check this out. You take the first thing, you square it, x squared. You take the second thing, and there's 2 of them. That's 2 times 3x, the a times b. And then you take the last thing, and you square it, which is b squared. That's plus 9. So then you get x squared plus 6x plus 9. Whoa, isn't that cool? I don't know. I don't think I did a good job explaining that, but that's okay. You can come to my office hours if you want to talk about Pascal's triangle. All right. Then once you're here, we only know a couple of ways that we can solve equations that have x squared in them. Number one, there's a very famous formula for. It has a song that's associated with it. Feel free to sing the song as you do it. And the second way is to factor them. Okay? So you got to get everything over here on one side, and then you can either use the quadratic formula or you can factor. But I'll let you solve and find a potential extraneous solution. All right. I want to just talk about this last one because we did this in class actually today, if you're watching this in my class. And it's really the same properties as solving those equations, but we do have a little bit more of a word problem thing. So I want to just tell you, if you're given a problem like this, what does it mean to solve an equation for a variable? I'll set it up for you, and then you can plug something in using one of these, okay? So the kinetic energy in joules, E, of an object depends on its mass in kilograms, which is called M. So we have energy, E, mass, M, and velocity, V, okay? The equation is this. V equals the square root of 2E over M. Well, if you're given the energy and the mass, you can find the velocity. But what if you're not? What if you're given maybe the mass and the velocity? So you need to solve this quote unquote literal equation, all right? And so in this case, if we solve this for E, this means get E by itself. Get E by itself, okay? And so I'm gonna do things to both sides of this equation so that E can get by itself on one side of the equation. First things first, it's trapped. It's stuck underneath this square root. I need to get rid of that, so I'm going to square both sides right away. And I'll end up with this. I'll get v squared from the v squared equals 2e over m. Well, I'm still don't have e by itself. I have some stuff that's stopping it. First of all, it's being divided by m. And so in order to cancel that division, I'm going to multiply by m. Okay? That means I'm going to get this. I'm going to get m times v squared equals 2e. Then if I want just e by itself, all I have to do is divide both sides by 2. And I end up in total with e equals m times v squared over 2. And there's my answer. Okay, I've officially got e by itself. So then if you were to give a question like B, calculate the kinetic energy, calculate E of a truck with a mass 2,500 kilograms traveling at 20 meters per second. Well, I know that this thing is M, this thing is V. We're solving for E. Then we would just type this into our calculator. E equals mass, which is 2,500, times 20 squared for the velocity, and then divided by 2. And then I'll get this. Let's see. What does it equal? I get 2,500 times 20 squared, and then I'll divide by 2. 500,000 joules. Holy moly. That's a lot of joules, I think. 20 meters per second is really fast, no? 2,500 kilograms is a lot, no? I don't know. 500,000 joules. That's a lot of energy. NRG. All right. That's going to be it. It's only 6 questions. I did less than 6 questions in this time frame, but I'm giving you 7 to do. I gave you a few of these to solve. I've given you a few of these graphing ones to do, but I did all these ones and then the front page. All right. Good luck with your review. Ask questions. Get these notes down. Take any notes that you want. Yeah. Have fun. See ya.